Hi everyone, my name is Finkel, and I'm the lead for compiler technology and programming languages at the Argonne Leadership Computing Facility. I'm here to talk to you today about how we're going to program Aurora, our upcoming supercomputer, at Exascale, using SYCL, DPC++, and a variety of other programming models. Before we start, I'm going to give you some background on scientific supercomputing, just so that we're all on the same page. Traditional scientific supercomputing is computing for large, tightly coupled problems. Large is important. It implies, in this case, both lots of computational capability, lots of flops, you could say, with lots of high-performance memory. But the tightly coupled is also important. It means that the computational density has to be high, because we need to connect all the different elements with a high bandwidth, low latency network. And as a result, we end up with unique architectural challenges, getting that much compute with that high of a density. Scientific supercomputing covers a large number of different scientific domains. At our facility at Argonne, we run problems from material science, from physics, biology, chemistry, engineering, and so on. All of these different domains are served by the one facility, and we have sister facilities at other laboratories as well. Across those different domains, there are common algorithmic classes. There's dense linear algebra, sparse linear algebra, FFTs, particle methods, and so on. Some of these methods are used across many different domains, and it's important to recognize that these different methods will stress the hardware in different ways. Some demand really high flop rates or high computational ability. Some demand really high performance from the memory subsystem more than anything else. And some demand high performance from the network more than anything else. The upcoming hardware that we're getting at Argonne, Aurora, as well as upcoming hardware at our sister facilities across the country and also across the world, are representative of machines that serve all those different scientific domains and classes of algorithms. When I entered this field some number of years ago, there was an ongoing debate as to whether the future of supercomputing would focus on many core CPU-based architectures or on architectures based on GPUs or other kinds of computational accelerators. While the jury is still out in some sense, all of our upcoming systems will use GPUs. So there'll be hot nodes, nodes with powerful CPUs that drive even more powerful GPUs as computational accelerators. Here you can see our map of upcoming systems across a variety of different laboratories within the US Department of Energy's computing ecosystem. Aurora is the system that we're getting, and you can see it's being provided by Intel and Cray, but other vendors provide other systems that are an important part of our ecosystem. Our upcoming machine is going to be provided by a collaboration between Intel and Cray, and will feature a sustained performance that is greater than 1 exaflop. Importantly, it will be a machine that is powered by Intel CPUs and GPUs. We'll have a large amount of system memory and a state-of-the-art interconnect that is used to connect all the nodes together. In addition, it will have a state-of-the-art file system that will provide unprecedented capacity and performance to our system. It's worth zooming in on the compute node for a moment. As I mentioned, it will have CPUs and GPUs. The GPUs are connected together using a low latency, high bandwidth interconnect on node. In addition, the architecture features a unified memory subsystem, allowing memory to be addressed across both the CPUs and the GPUs. And this has important implications for our programming model. It means, specifically and importantly, that our program model will be able to focus on providing data motion capabilities for high performance use cases, while allowing the unified memory subsystem to enable application data movement in cases where that enablement is important, but the specific performance of the transfers is not necessarily as important. Now, how are these machines, in Aurora specifically, programmed? One thing it's important to realize is that across the various pillars of applications that we serve, both traditional simulation, data analytics, and large-scale machine learning, all of these applications sit on top of a set of high-performance libraries, and in addition, compilers supporting parallel programming models, operating systems, workflow schedulers, operating system kernels, and so on. I want to highlight quickly that the internode programming model on these systems, the model that's used in order to take advantage of that high-performance network, is based on or programmed using MPI. MPI, the message passing interface, is the model of choice for doing the internode programming on large-scale HPC systems. But that does not address the programming of the intranode parallelism, and especially does not address that parallelism on GPUs. Before we move on to talk about how we will program that parallelism, it is important to point out that while I'm going to be talking a lot about C++ and C++-based programming models going forward, I should acknowledge that a large portion of our workload is still programmed in Fortran. This is modern Fortran, not Fortran 77 necessarily, but there is a large amount of it, and it is important for us to support Fortran as a first-class programming language on our systems. It's also true that most new code development seems to have shifted to other languages, mainly C++, but also Python and a variety of other choices. Now, Intel, who's providing our system, has released something that they call the oneAPI, which covers parallel programming models and high-performance libraries, as well as other interfaces. And that's the primary target for programming Aurora. I mentioned that a lot of the applications depend not only on parallel programming models, but also on high-performance math libraries. Intel, of course, will provide high-performance math libraries for our system, featuring some of the algorithms that were on the chart I showed you at the beginning, including things like Fourier transforms and dense linear algebra, and so on. In addition, libraries will be provided to support data analytics and machine learning workloads. And it's very important to understand that while many applications will use parallel programming models directly and implement many of their important kernels that way, they'll also depend on these provided math libraries for getting high performance on the system. Now let's talk about programming models proper. As you can see here, there are a variety of programming models that we expect people to use on exascale systems. Not all of these models will be supported on all the different systems, however, and on the other hand, some of these models are specifically designed to be portable across systems. And it'll be interesting to explore the extent to which these various models are and are not portable, both syntactically and performance-wise. One of the important models that we have on our systems is OpenMP. Perhaps I'll call it the second most important model. The applications that use OpenMP vary in base programming language. They could be C or C++ or Fortran. And as I noted, it's important that we support Fortran, and OpenMP is the primary parallelization model supported by Fortran. For C and C++ code, especially C++ code, there are more options, and we're going to talk about that in the coming minutes. For those of you who aren't familiar with OpenMP, it's a directive-based model. And here are some examples of the directives that are used for parallelization across GPUs. You can see they start with the pragma syntax element followed by OMP, and then a number of directives and other clauses. There's also a runtime library providing functions that the program can call, and environmental variables that control defaults. Importantly, our system is going to support data parallel C++, but it's a programming model that's based on SYCL. the standard from Kronos. SYCL is based on modern C++, and there are a number of different implementations of SYCL, including Compute CPP from CodePlay, IntelliSYCL, TriSYCL, HipSYCL, and so on. And across these different implementations, it's possible to run SYCL on a variety of today's CPUs and also GPUs from NVIDIA and AMD. DPC++ builds on top of SYCL and adds a number of features that are quite important for programming exascale supercomputers. This includes unified memory, and I discussed before that that's an important enablement feature on our system, in addition to providing support for reductions on named lambdas, which is important for being able to wrap SYCL and DPC++ using higher level abstraction layers, and subgroups, which are important for getting performance on many systems. Just to give you a point of comparison, here's a simple example using OpenMP in order to parallelize a kernel and execute it on, say, a GPU. You can see here that the OpenMP syntax is not extremely simple. You may, if you know about OpenMP, know that it's easy on a CPU to parallelize a loop using only pragma OMP parallel 4. But you require many additional syntax elements to get OpenMP to work on a GPU, and this includes data mapping clauses to handle data motion, in addition to various kinds of parallelism decomposition for the GPU itself. Here's a corresponding kernel for SYCL. You can see here that there are a number of different objects that are created. There's a work queue that is explicit in the code, in addition to the kernel that's being executed, being passed as a lambda, a modern C++ feature, and the use of this accessor, which allows a dynamic dependency graph to be constructed, and the kernel to have execution and, in addition, data dependencies. Now that I've given you a brief overview of the system and the models that will be supported, I want to talk about performance portability. I think this is an important topic in this context, especially as we talk about SYCL, which is designed to be a portable, perhaps performance portable, parallel programming model for a variety of different architectures. A performance portable application is one that's portable and also runs on a diverse set of architectures with reasonable performance. I think it's important to understand what our experience shows in the development of performance portable applications. You might think that you develop an application in the following way. First, you have a science problem. Then you choose the algorithms you're going to use to solve the problem. You implement and test the algorithms. You optimize the algorithms, and in the optimization process, take advantage of knowledge of some architecture and tools. And then when you're done, you have a high-performance code and you run it. However, that doesn't generally work. The problem is that the freedom you have to optimize the algorithms once they're completely fixed is generally not sufficient in order to solve the problem with the highest possible performance. There are various trade-offs that are made when picking an algorithm and implementation, including choices of basis functions and representations, regularization schemes, and solver techniques, trade-offs between involved degrees of freedom and those that are recomputed, and so on. These are choices that cannot be made by a compiler, at least not a compiler that's operating at a C++ or Fortran level. And so it's important to understand that while the creation of performance portable applications is certainly possible, it does mean that those applications tend to be highly parameterized, so that those various algorithmic choices can be exposed and used as part of the tuning process. Now, it's also important to recognize that the way people program applications is changing over time. If we reach back to around 2015, 5 years ago, and we look at what parallel programming models people were using on our systems, you will see that most people were parallelizing for CPUs, and they were doing so using OpenMP directly. A much smaller percentage of people were using any kind of abstraction library. But this is changing. We are seeing even greater adoption of OpenMP, but many applications are not using OpenMP directly, and abstraction libraries are gaining in popularity. At the Department of Energy, we develop at least two of these, and I'll note two explicitly. One is Raja, and the other is called Kokkos. Both of these provide abstractions around parallel execution, including on GPUs. They make use of C++ lambdas and other modern C++ features in order to provide a productive programming experience. Also, they can use OpenMP or some other compiler directive-based scheme under the hood, but are probably using an underlying programming model for each system directly to implement the backend for that system, such as DPC++ or HIP or CUDA. The development of those models is also influencing the development of standard C++ itself. And in C++ 17, the standard library has added parallel algorithms, which you can use much in the same way as you use the regular sequential standard algorithms, but now with the ability to specify the algorithm should be executed in parallel or vectorized. It's also important to realize that there's an extent to which the compiler can play a role in how parallel programs are implemented and executed, even at the level of the parallelism itself. You might think that it should be the programmer's responsibility to directly write code that is optimal across different architectures. And to some extent, programmers try to do this, but it's important to realize that there are constraints. Programmers use abstraction layers in order to manage development across large teams of programmers, and they might not be able to write optimal code directly. The code that has to run in parallel and that might benefit from running together might be in separate library components, for example. There are various kinds of optimizations that a compiler might perform on parallel constructs. It might, for instance, want to split loops or fuse them together. It might want to do the same for kernels, splitting them apart or fusing them together in order to optimize for minimization of kernel launch overhead or to minimize register pressure and so on. In addition, even providing a compiler with understanding of parallel constructs can greatly enhance the performance of code. The fact that the flow of a program is broken up across different kernels and so on can interfere with compiler optimizations that the compiler would otherwise perform. And having the compiler understand parallelism enough to get, say, better pointer aliasing results inside of a kernel based on data from the code outside of the kernel can yield significant benefits. In addition, it's important to realize that the optimization of code and kernels is not simply limited to changing loop nest structures and so on, but the data layout is very important. The layout of data has a large effect on the structure of the kernel, of course, and the efficiency with which the data can be accessed. And as you can see here, Kokkos, which is one of the C++ abstraction libraries I mentioned earlier, provides a way of customizing the data layout in an abstract, performance portable way. And this is important. The performance that you can obtain using the optimal data layout can be much, much greater than the performance attainable using a data layout that's tuned perhaps for a different architecture. So where does this leave us? Well, we discussed 3 different models: OpenMP, DPC++ based on SYCL, and Kokkos and Raja. OpenMP started as a set of relatively simple directives and runtime function calls. Yet, the complexities of dealing with GPUs, data movement, and other aspects of accelerators have caused these simple directives to yield to more complicated ones. DPC++ and Kokkos and Raja are based on modern C++. And as modern C++ adds features to allow simple cases to become simpler, the usage of these models also becomes simpler over time. The default execution model is also important to consider. both OpenMP and Kokkos and Raja, based by default on a fork-join-based model, especially for accelerator-based parallelism, although these models support task-based parallelism as well in some cases. DPC++ is based on an explicit manifestation of parallel work queues, and this is probably better for expressing scalable parallelism, although that remains to be seen. We saw that it's important to consider the extent to which a compiler might be able to optimize parallel constructs in a program. This ability is most directly accessible for parallel programming models that are, in fact, part of the compiler, like OpenMP. For wrapper libraries like Kokkos and Raja, it's going to depend on what the underlying layer is. And for DPC++, this ability is probably lower than for other alternatives, especially because the dynamic work queue structure obscures the structure of the parallelism in the program. Now, on the other hand, we saw that highly parameterized code is generally essential for creating performance-portable, high-performance applications. And the ability to integrate with highly parameterized code, especially using templates in C++, is maximized for modern C++-based programming models, such as DPC++, and also things like Kokkos and Raja, whereas the ability to do that with something like OpenMP is much reduced. We saw that data layout is an important aspect of creating high-performance applications. Kokkos and Raja provide this kind of support, and I expect we might see this kind of support in DPC++ and SYCL in the future. It's also important to understand that all of these models currently are very host-centric. They start execution on the host, and the host is assumed to be there as a kind of central coordinator between all the different kernels and execution that's going on. But none of these programming models really provide good support for non-host-centric computation, where the CPU does not serve such a central role in the system, and data, and perhaps even execution, can be triggered from one accelerator to another directly. So, to conclude, future supercomputers will continue to advance scientific progress in a variety of different domains, in addition, of course, to pushing the bounds of computing technology. Applications are going to rely on high-performance libraries, as well as parallel programming models, in order to attain high performance on these systems. DPC++ and SYCL is going to be a critical programming model on future HPC systems, especially on our upcoming system, Aurora. We will continue to understand the extent to which compiler optimizations assist the development of portably performant applications. First is, in some sense, the ability to explicitly parameterize and dynamically compose the implementations of algorithms. There's a trade-off there. The more freedom you give the programmer to explicitly choose how the program executes, the less freedom you give the compiler to change it, and vice versa. It's a fundamental trade-off in the design of programming languages and libraries. Parallel programming models will continue to evolve. Support for data layouts and less host-centric models will be explored in the future, and I expect we'll see significant developments in that space. With that, I'd like to thank the United States Department of Energy, Argonne's Leadership Computing Facility, and the DOE Exascale Computing Project for supporting a lot of the work that we've been doing over the past few years. And in addition, I'd like to thank the research scientist staff at the Argonne Leadership Computing Facility, Computational Science Division, and our other sister divisions within Argonne for all of the effort they have put in to exploring programming models and other aspects of how to program future systems.